A warm welcome to the parallel session on slope stability and landslides here in South 2. I am delighted to invite our esteemed chair, Professor T. Tyagaraj, to the session as the chair for the session. I welcome Professor Tyagaraj to preside over the session. Thank you.
Thank you. So good afternoon, everybody. So welcome to this parallel session on slope stability and landslides. So we have 9 contributing paper presentations, and before that we have one theme lecture. So I think 3 people have not turned up. I think maybe they would have come. I'm not sure. So for theme lecture, 15 minutes, and for the paper presentations 10 minutes. So since we already lost about 16 to 17 minutes, so without losing much time, we'll start the thing. So please restrict yourself to 10 minutes. So the theme lecture is on a study on wind erosion mitigation of fly ash in disposal sites using geopolymerization. This will be given by Professor Hari Krishna Padawala. He is a professor at NIT Warangal, right? So, and he was also a dean prior to that. And I was a colleague for some time in 2006 and 7. So, with this brief introduction, I request Professor Hari Krishna to start his lecture.
Good afternoon to everyone, especially Professor Tyagaraj and friends. Maybe after afternoon it may be difficult for us to have a wonderful talk, but I'll try my level best. Hopefully you also will enjoy this. And we have done recently a study on, this is the talk what we have planned. We do have NTPCs near NIT Warangal. There is a big in Telangana itself, NTPC Ramagundam, where we had a big 1,200 acres of land occupied by fly ash. And we do have little collaboration in terms of consultancy, where we had this issue being. Okay. Not working. Okay. This issue of this erosion of fly ash, mainly by wind, sometimes by water, which is causing a lot of issues to the surrounding places. The nearby people are complaining to NTPC, saying that their health and even the food is getting contaminated. So we tried a little bit. I think it's not moving. Oh, got it. Okay. I don't know why it is not moving here. Okay, this is good. At least, okay. So this, when we think of, it's not moving here. No, this is Adama. Okay. No, this is not the one. Okay, this one. This is not functioning. So when this point, no, it is not moving here. There it is moving. When we think of this power generation, especially by thermal plants, where coal is being used, and this generates large volume of fly ash in India, especially each year, around 50 crore tons of ash is being generated. Frankly speaking, not even 1/4 of it is being utilized, although it has a lot of applications. And whenever we think of the capacity or the quantum of ash being generated, whatever it is generated and whatever we are using is very less and very minimal. Yeah, this is whatever we have seen, whatever many of you might have come across. Any plant will be having huge lagoons, hundreds of acres. This has gone into thousands of acres of land being occupied with ash, dumped, thousands of tons of it. The problem here is whenever it becomes dry, of course, when it is in a little wet condition, there is not much of an issue. When the temperatures in Telangana especially goes beyond in summer for 3 to 4 months more than 45, they may not report 50, but it touches sometimes. So it becomes very dry, and under dry condition, it will be very susceptible for erosion. It inundates nearby areas with lot of thick ash. So we have gone for this wind erosion aspect. So whenever they are, fly ash particles are very fine, and of course they are lightweight, and they are very susceptible for wind erosion, especially as I have mentioned when they are dry and when they are exposed to the surface. And there is a lot of air pollution. And whenever this case of high-speed winds, they will disperse these fly ash particles longer distances, maybe kilometers also, and they will be deposited on the vegetations, whatever cultivation they had, and water bodies, and disrupting the ecosystem. Mainly, the other important thing is they had a lot of health issues, respiratory problems, because they are inhaling that one, and of course, they are reducing the agricultural potency also. Yeah, this is one, may not be that good, but this is all ash in air floating, maybe just because one vehicle is moving nearby that area. Now, literature says there are some good proven methods for mitigating this issue, like whether we can go for spraying of water, maybe depositing some amount of soil over it, or we can go for some planting. Of course, recently we are going for surface cured dust control. Whenever we think of water spray, yeah, it works out to some extent. But only issue is when there is a water scarcity in places where there is no water, this becomes a very big problem. It's simple methods, but requires significant amount of water, which is a challenge. Whereas coming to soil cover, and there also we need to have transportation of so much of soils. Whenever we think of even highway constructions, we are seeing so much of material getting is a very difficult thing. Of course, this is another easy one, but the problem is it takes some time to get the entire plantations being covering this entire thing. So it's also having some limitations like this. Whatever proven methods have some limitations. Friends, this one, surface cured dust control, we thought of making the surface layer just like we have skin over the flesh. If we can make this one little hard enough so that it will not fly. That is a basic idea. So we thought of having some spraying of active materials which will react with loose particles on the surface of fly ash sites to form a solid layer with a certain strength. That is the basic objective with which we worked. Of course, this is some of the techniques they adapt whenever they have cut tile, they go for curtains so that the ash will not fly. And of course, they will go on spraying water. That also sometimes it works. Yeah, whenever we think of this EACP enzyme-induced carbonate precipitation, we will go for this surface curing with the geopolymerization technique, wherein we add some chemicals. It can be sodium oxide, sodium silicate, like that. They have a mechanism of making carbon condensation, and then it will go for hardening of the surface, hardening of the material, so that it will have proper gel, so that it becomes a thick and robust technique, robust layer. So as all of us know, this geopolymerization is a process where this aluminum silicate materials react with alkali activators that will form a hardened cement-like material to some extent, like geopolymer. And this shows significant promise as a long-term erosion control solution for the ash deposits because of two things. This has long-term stability along with some sustainable aspects here. Friends, this is the ash what we got from Ramagundam, NTPC Ramagundam, which is one of the popular plants in South India. And with a specific gravity of 2.18, of course, it is a silty sand with good amount of sand and silts equal almost, and with a very low UCS value of 0.13 MPa. And then we have gone for, this is the particle size distribution. This basic chemical composition turns to be class F fly ash because of its low concentration of calcium oxide and huge amount of alumina, silica, and ferrous oxides. So it turns out to be class F based on this chemical composition. Then we have taken up two materials based on literature with so many publications. For geopolymerization, we have gone for a combination of two things. Of course, we tried initially only sodium hydroxide independently with some molarities. And then we have thought of adding sodium silicate so that it will be long-term effects will be there. So we have taken sodium hydroxide and sodium silicate solutions for this. And we have gone for as a basic test of getting the strength of it UCS, which is a very easy one and very comfortable. Of course, there are some literature to combine or to get the value or the propensity of erosion with the UCS. We have gone for different molarities of sodium oxide, 8, 2, 4, 6 to 8. This is based on literature we tried. And of course, in the second phase, we have gone for not only sodium oxide, we have taken sodium silicate and with the different proportions of 1:0.5, 1:1, 1:1.5 and 2. And we have gone for different curing periods just to know the effect of curing on UCS 1, 3, 7 and 14. And in the phase 1, we prepared, as I have already mentioned, different samples for UCS with the different molarities of NaOH. And we have, of course, gone for OMC and MDD. In the second phase, we took, along with sodium hydroxide, we have gone for sodium silicate with the different proportions as we have seen with contribution of 0.5, 1, 1.5, and of course 2. And here we had one wind tunnel in NIT Warangal. So we took a test wherein we'll prepare the sample, keep it in the wind tunnel, and we'll go for different velocities, 10 meter per second, 20 like this. We thought of checking this one. We have gone for a wind tunnel test, and it's a suction type subsonic wind tunnel we had. And we have gone for some trays of 15 by 15 by 5, and we have sprayed along this ash on a tray these different types of alkali solutions, and we have gone for 3 different types of velocities, and aerobability we measured. That's it. This is the wind tunnel test that is available in Mechanical Engineering Department of NIT Warangal, wherein we have kept the sample here, and we kept the sample here in a tray like this, and we allowed the wind to blow at different speeds, and we checked the layer, whether it is getting eroded or not. So the surface, of course, this is what I have already mentioned, this one. This is almost like a repetition. Yeah. Then just to know the molecular biology of it, we have gone for SEM test, and just to understand the morphological changes, whatever the bonding we had and formation of what type of gels that are laid, which is influencing the material durability along with resistance to erosion. Of course, the crust samples were collected from the surface of geopolymer treated fly ash, and we had different coatings of this also. Yeah, this is the SEM test setup we have along with the EDS unit in CSRS lab in NIT Warangal. Yeah, coming to the results, and as you can see, as I mentioned, we had a UCS of 0.13 MPa only, but when we have gone for a chemical of NaOH with different curing periods, you can see there's a 25 times increase in UCS value to up to 3.5, something like that from 0.13. And when we have gone for even sodium silicate at different proportions of 1, 2 or 1.5, it has gone to around 9 approximately. So it has increased to 70 times with respect to its original strength of untreated fly ash. And this is the erosion. We have gone for rate of erosion. And when we compare to, this is a case of untreated fly ash, different wind speeds of 10, 20, 30. And as you can see here, when we have gone for different proportions, this is 10 meter per second, and different ratios we have gone for different curing periods, 1, 3, 7, 4. Of course, naturally 14 days curing period has given very, very less erosion when compared to these high erosions. Whatever, 10 meter per second, if you see, this is 7,500, whereas it has come to 166. There's a drastic decrease in erosion, even at 10. Of course, when we've gone for higher speeds of 20 meter per second and 30 meter per second, there is also a drastic decrease. It's only 6.5 when compared to my untreated condition of 14,000. So that is that there is a decrease of around 90% decrease in the erosion of this. This is the trace, different 4 trays for 4 different proportions we had at 30 meter per second. And as you can see, there's a lot of erosion here. There is not much of erosion when you have gone for higher percentages of it. Of course, even SEM, when we have gone for, there is a good amount of gel formation for 6 molar based on our findings. Therefore, we have selected 6 molar even for sodium silicate addition also. And we have calculated the thickness of crust, how much layer it is getting formed. And when we have gone for with different molarities of NaOH, you can see here 4.58 and it is 19.4, almost 4 times increase with molarity. And it's a very good thick. And of course, the problem with NaOH is it is little porous. It is not, although it is brittle, we can easily be able to break it. But friends, when we have gone for sodium oxide along with sodium silicate, although the thickness is less, but that much of brittleness is it's a little strong. You cannot easily break it also. That's the kind of invention, the kind of findings what we had. Although the thickness is less when compared to only NaOH, this is showing little higher one. So coming to the conclusions, the present study investigated the erodibility of surface treated fly ash against wind erosion. Of course, this polymeral stabilization of fly ash was evaluated using UCS as indirect method and wind tunnel testing as a direct method to assess this erosion aspects of fly ash. The compressive strength increased significantly when treated with sodium hydroxide and sodium silicate. Friends, the erodibility of untreated fly ash decreased by 99%, which is remarkable when treated with 6 molar, of course, with different proportions of sodium silicate. Finally, the microstructure analysis revealed the formation of alkali-activated cementitious gels formed due to geopolymerization, which contributed to the formation of the crust. Friends, the resulting crust significantly protected the surface from the wind erosion, resulting in a dramatic reduction in the erodibility of fly ash with wind. These are the references. Thank you very much. And I thank the organizers of Geotech Asia for giving me a chance, and my friend and colleague for bearing with me. Thank you, Raj.
Thank you, Professor Hari Krishna. Any questions? Couple of questions? Big questions?
Yeah.
Actually, it's not related to geotechnical, but in Philippines, we usually, the plants were required to comply with the environment. So my question is, in relation with environmental impact of this method, what are the considerations?
We haven't gone in that direction presently. It's a PG project where our aim is to avoid the erosion. Yeah, as you're telling, we have to think of that one as the next aspect. We have to study that one, please. I have to admit that.
Thickness of your tray sample, the same in all?
Sorry?
Thickness of the tray sample.
Yeah, we have made uniformity, sir, for all
So
the...
if you change that, there will be change in that also.
Sorry?
If the thickness increases of
Yeah.
that complete fly ash, because when you go in the field, it is in meters.
But one issue here is, as I have already mentioned, if the surface maybe few centimeters is stabilized, it will not get eroded. It will not get eroded.
It has nothing to do with the height of your total height of.
Only thing, if the top layer is eroded, then we can think of bottom layer possible for erosion. If the top layer itself is not eroding, there is no question of going down.
No, we have tested like this for this Gorai thermal power plant, Nagpur.
Sir.
And we observed that if the thickness is more, then it is erosion will be less. That's what we observed there.
Okay, we'll go for different thicknesses.
Yeah,
Here
different
we have
thickness.
maintained the
Yes,
same
yes,
thickness.
yes,
We'll
yes,
go
please.
for that
Yes,
one.
okay,
Thank you,
thank
sir.
you, thank you.
Thank you. I have one quick question.
Sir.
Maybe what about durability? Let us say that you have a rainy season. So is
That
it
is the second
durable?
test what we have done.
And maybe leaching of
Yes.
those.
That also we have completed, but we have not presented in this. Thank you, sir.
Thank you. Thank you very much for the interesting presentation.
Thank you, sir.
Yeah. Is there any member later on? Is there any? So next we have, as I said, 9 contributing chapter paper presentations. The first presentation is on calibration of open pit mine slopes, models through forensic investigation of actual failures. This will be, there are many authors in that. So it will be presented by Andrew Jean. Yes. I request Andrew Jean to present. Maybe after 8 minutes, I will give you a signal to conclude. Thank you.
Let me exit this first. Oops. Okay. I'm okay. Presentation view. Okay. Okay.
So I will be speeding things up since we have a little time. So good afternoon, everyone. I'm Andre Jean de Guzman Pineda. I'm an engineer in Philippines, along with my co-authors around here, but mainly John Michael Tanap is here in front of me. So the paper is entitled Calibration of Open Pit Mine Slope Models Through Forensic Investigation of Actual Failures. So this is the outline of our presentation. So as an introduction, open pit mining is a method of extracting mineral resources directly from the surface, excavating downward to further expose deposits and producing open face slopes. So however, this method is often associated with geohazards such as slope, instability, which possess several risks. So therefore, studies have highlighted the importance of comprehensive monitoring and slope stability analysis during mining operations. So we use limit equilibrium method, or LEM method is typically employed for this stability analysis. So for the site description, an open pit mine in the Philippines is presented as a case study. So key characteristics of the site is the evaluation of the excavation reaches approximately 200 meters below sea level. So also the stratigraphy of the mine walls features multiple parallel rock layers characterized by cyclic sequences of sandstone, siltstone, mudstone, claystones, and coal seams. So above this sequence is a formation of the horizontal layered sequence of limestone, highly permeable coral layers, and recent marine deposits. So with this site conditions, geohazards are identified. So operational mining activities resulted in substantial alterations in the terrain and some massive slope developments or movements. So excavation exposes the rock bedding planes, creating planes of weakness that potentially lead to mass movement. The most prevalent hazard within the pits is slope failure, manifested by formation of tension cracks, creepings, rock falls, and debris flows. So in addition, one key feature of the mine site is that its open face slopes are already below sea level. Thus, the in situ material are fully saturated, as is evident from the observed seepage in the pits due to continuous percolation of groundwater through the permeable strata. So more importantly, the existing cracks worsen as seepage continues, thereby jeopardizing the stability of concerned areas. So with this, it is recognized that several assets, mainly personnel and equipment, are affected by prevailing hazards and thus were identified as part of the risk mitigation program. In recognition of these risks, instrumentation, regular monitoring, and strict compliance with protocols are being implemented. For the succeeding presentation, we will be doing the baseline analysis. So for the baseline slope models, due to the limited number of strength tests, our analysis primarily relied on the data from exploration core boreholes or core samples. Due to the laboratory testing was constrained, we performed a baseline analysis and calibration using combined approach. Number one, properties derived from the available core samples. Number two, we did back analysis of actual slope failures to refine and validate these properties as shown. So these are the properties, baseline shear strength parameters. This combination provided calibrated strength parameters suitable for stability assessments while highlighting the need for additional in situ testing, which is if possible. So since the open pit mine is situated below sea level, the analysis was modeled under fully saturated conditions. These assumptions provides conservative approach to account for potential groundwater influence on the slope stability. So now for the baseline analysis, as you can see in the figure, it shows that potential deep-seated failure, approximately 250 meters deep. This differs from the on-site observations, which indicate movements are relatively shallow depths within approximately 30 meters. So this is the 30 meters, the blue shaded one. So as such, sensitivity analysis is needed to establish a more appropriate and realistic set of shear strength parameters and subsurface conditions. So What is sensitivity analysis in slope stability? It is a process in model calibration and validation used to determine and explore the influence of variability and uncertainty of input parameters in the stability of the model. So next is, it is coupled with forensic investigation of actual failure on site. And our objective of the process, number one, is to refine the material properties of the deeper layers in order to eliminate the unrealistic deep-seated failures. Number two, to modify and the parameters in the upper layers where most of the failures have been observed because of or based on the approach and adopted for the deep layers. So here's our sensitivity analysis process. So phase one entails the sensitivity analysis of the UCS, or uniaxial compressive strength of the deep layers at depths of below 30 meters. Considering this particular site, 30 meters is generally undisturbed, which is the disturbance factor is 0. Following this, phase 2 was developed to account for the level of exposure or disturbance of the upper layers to on-site activities such as manual excavation. This accounts for higher disturbance factor, which is 0.9. Lastly, phase 3, we subdivide the top layer to analyze a phase 2. This results in total of 3 geological zones. So for better appreciation, here is the figure that shows the delineation of zones. The 0 to 20 meters, that's the blue shaded one. The zone 2 is the 20 to 30 meters, which we prefer as a transition zone from the upper to going to the undisturbed zones. And the undisturbed zone is the zone 3, which is below 30 meters. So next is the subsurface layers, where again we're divided into assigned disturbance factors, and UCS values were per zone. Sorry. So similarly, trial runs are conducted using the updated modified parameters. The slope models incorporate the previously described 3 zones, which different of set of parameters. Then from the analysis, the obtained factor of safety are found to be relatively consistent with the site observations on site. So for the conclusion, failure surfaces were confined to the upper 20 meters, highlighting the importance of detailed zoning in the analysis. Reliance on reference values alone is not appropriate, so sensitivity analysis and forensic investigation of on-site failures were necessary. So reliable slope stability assessment, continuous refinement, monitoring, and integration of observational methods, comprehensive investigation, strict monitoring, and careful assignment of geotechnical parameters ensure reliable assessment consistent with field observation. And lastly, the observational method proves effective and highlights the importance of regular slope stability with instrumentation and monitoring. So here's our references, and thank you.
Thank you. Couple of questions,
Hello, sir.
please.
Thank you. Maybe I missed that part. What was the basis for making those zones 0 to 20, 20 to 30?
All right. So that's the phases of the sensitivity analysis. So in the on-site observation, the slope failures is not particularly going down to more than 30 meters. But an on-site observation, it's only within 30 meters of the slope. So going back to here. Here. So in the analysis, the resulting values are this deep-seated, which is more than 200 meters. But in the on-site observation, it's more likely probably in the shaded area of blue. That's the 30 meters. So with the sensitivity analysis of doing the phases, we have compiled the possible and most likely the probable failures that will occur on site, which is consistent with the on-site observation. Thank you.
And about the disturbance factor you used for those analyses, I think the book of GSI doesn't have 0.9 or something in between. For erratic type of blasting, they have 1 or something, and you used 0.9, right?
Yes.
Did you use 0.9 to be on the conservative side?
All right. So regarding with the disturbance factor of using 0.9, we go hand in hand with our geologists on site, and they prefer using the 0.9 disturbance factor since some of the equipments is quite too disturbed of more like a value of 0.9. So with that, thank you.
Other questions, I believe? Thank you for the nice presentation.
Thank you, sir.
You can interact if you have any other questions.
Yes. If you have any other questions, you can cut. Thank you.
So we have the next presentation is by Ratnakar Ramesh Mahajan. This is on design and construction of hybrid reinforced soil slopes for railways.
Thank you. Oops. What happened?
You have two presentations, right?
One.
The other one?
The other one, Jalukas Padar will be presenting.
You are presenting this one?
I'm presenting this. Yeah. Okay. From beginning. Yeah. Clear? Okay.
Please.
Okay. Very good afternoon to one and all. I'll be presenting on the design and construction of a hybrid reinforced soil slope. The terminology hybrid is used for two reasons. One, in this project we have used the two types of reinforcement together. One is the polymeric, which is geogrid, and another is the hexagonal mesh, which is made up of steel wires coated with a polymeric coating. Apart from that, conventional reinforced soil structures is typically built with the soil and the soil reinforcement. However, in this project we have combined it with the soil nailing. So it's a mixed hybrid structure that's typically called as the shored reinforced soil structure. This project is very well known in India, even for our friends from abroad. This is a Udhampur, Srinagar, Baramulla rail link project, which is very strategic project connecting India with the Kashmir. In this project, actually, there are a number of valleys which were required to be bridged, and the client, Northern Railway, had decided to use the bridges at multiple locations. One of the famous bridge, Chenab Bridge, you must be knowing. It is on the same project. The another very famous bridge, equally very important, but I think very few people know, is Anji Khad Bridge. It's also a very interesting bridge. The structures what I am showing is very just close to the Chenab Bridge. This alignment is in Himalaya, so it is passing through a very challenging geology. Here basically loose conglomerate, clay, silt, and let's say a crushed material that's being observed. The alignment is passing between the hills, specifically Chenage 42,872, 42,940, and this is referred as the bridge 40. So the number bridge 40 comes because there are serial number bridges 1, 2, 3, 4. This location bridge was proposed. However, in this project, number of tunnels have been constructed. As a tunneling operation, you get the tunnel muck, and disposal of this tunnel muck is a challenge because from environmental point of view, you need to contain this tunnel muck in a such a way that it doesn't contaminate the natural water sources, it doesn't damage the environment around it. So the client had a challenge to contain such a huge amount of tunnel muck. Of course, at this location, we had proposed instead of a bridge, let's go with a filled structure. Let's use the tunnel muck and build an embankment here. So it was a win-win situation for client because they are saving a lot of land which would be required for storing this tunnel muck. At the same time, that muck is freely being used for the construction of this valley to be filled with. That's where here the reinforced soil slopes have been proposed using geosynthetics. Here the height of the reinforced soil slope is 50 meters. For your information, Indian Railways still have not adopted reinforced soil technology as extensively as national highways. And this was another challenge which we faced a lot to convince the railway officials. Railway officers, they are typically following their guidelines. They refer as the RDSO. Okay, that's the organization which makes the standard. So it was a tough job. In this project, the photograph is self-explanatory. You can see here it's a bowl shape, and the rock here was fractured dolomite. Of course, some details about the core recovery and RQD is given, but more or less this is very highly sheared and fractured material. Here the mechanical drilling was done up to 40-meter depth to understand what kind of strata is. So I have added some photographs for the understanding that the material which is getting excavated, the tunnel is hardly 10 meters from here. So the photographs what you see on the left side is a tunnel, and it's the same strata which is there. And when it's being excavated, crushed, it's a very aggressive material. And geosynthetics have certain limitations, especially if you are using very coarse or harsh material. The material has to be really durable to take care of this kind of damage. Here, being a bowl shape and being a 50-meter tall structure, if you just do a simple calculation for reinforced soil structure, a rule of thumb, 60 to 70% of your height is the reinforcement length required. So you would require 30 to 35 meter long reinforcement length, but space is not available. That's where we have combined the soil nails. So back of the slope we have used the nails, and then in the front we put the structure. Of course, for designing this kind of structures, the only guideline that time for this project was FHWA. That was not even guideline, a research document. However, being a part of the textile BIS committee, for your information, we have come up with a document which even covers now design of such structures. In this project, we have used the stone fascia and a green fascia. The reason for that was to provide the environment back, the greenery, which due to anthropogenic activity we have disturbed. So here we have used the high strength geogrid paralink with a stiffness range of 1053 to 4232 kilonewton per meter. The anchors used were continuously threaded anchors, yield strength more than say 670. These anchors basically stabilized not only the slope, but during excavation the stability of the slope had to be ensured because it's a 50-meter tall structure we are building. The design followed the limit equilibrium approach as per BS 8006 and FHWA. As I said, the document for showed reinforced soil is not available, but we borrowed some portions from that. Another challenge here was about the live load to be considered. So here 25-ton axle load was required to be considered, and we converted into a live load of 75 kPa. Actually, this is very high. If you really do the calculation, it could be 30-40 kPa, but using dynamic augment, and on top of that, officers wanted some more factor of safety, so around 75 kPa pressure was considered. Seismic zone falling in 5. As per IS 1893, that seismic zone parameters have been considered. Typically for reinforced soil structures, fines passing through 75 micron has to be less than 15%. Friction angle minimum 30 degrees and PI less than 20. But fortunately, we had a tunnel mug which was very, very coarse and granular, so that was not an issue. Here, while designing, the approach followed was first the cut surface was analyzed with the soil nails, and then the reinforced soil structure was analyzed all together. So it's a three analysis was done. One, cut slope as it is. Second, cut slope with nails. And third, the reinforced soil structure, simulating the construction sequence also. So the geogrid spacing here was kept as a 0.8 meter vertical spacing, and the layers were compacted at a 0.3 meter maximum compacted thickness. This is the top view of the bridge 40. You can see very clearly a bowl shape here. At the same time, you can see the, I think, yeah. Here you have a big culvert which is coming. Actually, this culvert is carrying lot of subsurface water for 6 kilometer long tunnel. And till now also, this is almost like 8 years has happened, the flow has not reduced. It is continuously carrying the water. This is the green fascia that's being adopted. Okay. This is the structure almost close to 40 meters. On the right side is the culvert. On the left side, the merging of the structure with the natural slope was done using a stone fascia. The reason for that, when you have rainfall, possibilities of soil erosion would be there. In this project, the top portion of the embankment is 1:2. However, railway officials said, because 1:2 slope, actually you don't need any reinforcement, but they said this is being a first kind of thing, put your reinforcement there, so we have put additional reinforcements here. And the purpose of embankment on top was railway officials very
1.5 minute.
yeah, sure. To have the safety point of view, this was being put. So these are the photographs of a stone fascia and green fascia that's under construction. And this is what fascia after construction. This is after 6 months. And this is a trial which was done on the, I hope it runs, I don't know. Yeah, this was the trial which was done on the same structure before it was inaugurated by Honorable. The tunnel what you see, and on the left hand side, valley side, there is a structure there. Okay. So with this, thank you very much. If you want to know more, we can interact and you can note down by email address.
Thank you. Thank you for a nice presentation. A couple of questions, anything? Okay, it's very clear, I think.
Thank you.
Yes, we'll move to the next presentation. It's on volcanic ash clay and risk of catastrophic landslide. This is by Mizuki, and co-authors are Tomohiro and Tobita.
Okay, good afternoon, everyone. I'm Mizuki Kunisawa from Kansai University, Japan. Today, I am present the catastrophic landslides of volcanic ash clay. Okay, here is the background. In 2011, Tohoku earthquakes happened in Japan. Due to this huge earthquake in Shirakawa, Fukushima, slopes composed of volcanic deposits collapsed. This picture is a Hanoki-daira landslide. This is a mega landslide. Due to this landslide, 13 people lost their lives. And this landslide slope is gently sloped with an inclination of less than 30 degrees. So this is a high-risk hazard. Okay, now I explain the formation of this landslide process. There are volcano and original ground. When the volcano erupted, there are pyroclastic fall and flows. The flow and falls, then again eruption, flow and falls. And then now this is the original ground, the volcanic ash area. When the erosion making the slope, this slope is gently sloped. When the earthquake happened in this slope, the seismic motion due to making the slip surface. In this slip surface is firstly a weak layer, like this. Then the soil mass moving to this toward. This is a very big landslide. So in this research, we defined this type of the landslide is a catastrophic landslide, the phenomenon in which material slides down gentle slopes with high fluidity and gradually breaking apart and spreading. Also, this catastrophic landslides occurred in Indonesia and Japan. This is Padang earthquakes, and right side is Hokkaido Eastern Iburi earthquakes. And this, due to this catastrophic landslides contributing the halloysite. The halloysite is a clay mineral, and this is a halloysite formation of halloysite. And this is a picture in this halloysite making old weathered zone. Upper is water flowing and pumice area. This halloysite is one of the contributing factors to catastrophic landslides. So in this study, we conducted the field and laboratory investigations to determine the geotechnical properties of halloysite-rich paleosol. Okay, we conducted this site in Nishigo village in Fukushima, Japan. The SR means the Nath Shirakawa deposit, and we found the SR8 layer. So this layer is containing the halloysite. This is SR halloysite containing layer. This layer thick is 70 centimeter and could exhibit a lighter color, a relatively white color. And this layer deformed easily upon touch, displayed a creamy texture. And we conduct the soil sampling. Sampling site is this picture, the barrel-shaped outcrop. This is a water zone. And we collected the block sampling halloysite-rich volcano ash soils. And we conduct the field test. We used the soil strength probe by Sasaki 2010. And then we conduct the soil penetration test to convert to SPT N value and Bacon test. Here is the results of N values. We conduct the horizontal penetration test for SR8 layer. This SR8 layer means a halloysite containing layer. The results show a relatively low SPT N value. And this is a Bacon test. The SR layer is cohesion is 3.29 and friction angle is 9.414. Compared to the past research, different regions by Chigira, cohesion is almost the same, but the friction angle is twice times. And here is the geotechnical properties. In this study is here the SR8 layer containing halloysite. The water content is very high, over 100. And the leakage limit and the plasticity index is also high compared to the past research. Also, the 119 is water containing layer in this research is even with little rainfall, but high water content. And we conduct the unconfined compression test of SR8 clay layer. Case 1 and case 2 is undisturbed, and case 3 and case 4 are disturbed samples. Method of disturbance dropped the specimens from 1.5 meter in a plastic bag. In case 3, drop time is 5 times, and case 4 is 30. Here is the results of unconfined compression strength. The undisturbed specimens, case 1 and case 2, the average is 16.4. Compared to the generally marine clay, 30 to 80, this SR layer clay is very low strength. And disturbed specimen, case 3 is 8, and case 4 is 2.7. And in case 4, 86% reduction compared to case 1. So this is a sensitivity ratio, case 3 and case 4. Due to this, the results, this SR layer clay is very low strength and very high sensitivity ratio. So SR layer, SR8 layer containing halloysite is very sensitive clay. The disturbance due to seismic motion may greatly reduce ground strength. Okay, and finally I show this same figure in introduction. The catastrophic landslides have the potential slip surface, like here, between the upper and down side. And this layer is pyroclastic material containing halloysite. In this study, this slip surface layer is SR8. And when seismic motion happened, the slip surface making here and breaking apart and spreading. This is very huge landslides. So we use a catastrophic landslides. Okay, finally, here is the conclusions. We investigated the SR layer. In Shirakawa, SR layer is a halloysite-rich paleosol. And we present the 3 findings. First is the weak soil characteristics and high water retention. Finally is strong sensitivity of these halloysite-rich containing soils. Also, in India, there are some volcanic regions. So there are some volcanic regions means they have the potential risk of catastrophic landslides. So this is the very important findings, not only in Japan, but also in the world, including India. That's all my presentation. Thank you very much for your kindly attention.
A couple of questions. No? I have a question on sensitivity. Can you go there? I think you have combined the cases 2 and 3 and something you did that.
Okay.
Can you go to that slide?
Yes, here.
What is that? I could not follow. Case 1, case 2 and
Yes, case 1, case 2, and case 3, case 4.
Okay. For example, the 2.42, is it corresponding to case 1 or case 3?
Yes. Case 3 compared to case 1 is sensitivity ratio is 2.42.
Or you are not taking with respect to undisturbed versus disturbed? Or how are you taking that?
Here is undisturbed and disturbed specimens.
Okay, it's not clear. We can discuss later. Thank you. Thank you. So we'll move on to the next presentation. It's by Tulasi Ram Bhattarai. It's a comparative study on machine learning models to predict landslide susceptibility. Yeah.
Good afternoon. I'm going to present my research on comparative study of machine learning models to predict the landslide susceptibility. I'm the PhD student at Eime University, Japan. It's not working. Okay. Sorry. These are the outline of my presentation. I will start with introduction, research gaps and objectives, study area, dataset used for modeling, methodology, result and discussion, and finally conclusion. Basically, coming to the landslide susceptibility, what is the landslide susceptibility? The landslide susceptibility is the likelihood of landslide occurring in an area depending on the local terrain conditions, estimating the where landslide are likely to occur. Means the factor controlling the occurrence of previous landslide also control the occurrence of future landslides. So this is only the where component of the landslide hazards. Means in a spatial domain we are finding the probability of occurring the landslide. And then the triggering factors may be the rainfall, snow melt, water level changes, volcanic eruption or earthquake shaking. As we know, the mountain terrain are highly vulnerable to the landslides. The traditional mapping methods, basically the statistical and empirical methods, often miss to capture the nonlinear and complex interaction between the landslide conditioning parameters. And then nowadays, the GIS and machine learning techniques provide more accurate and dynamic tool for this kind of hazard assessment. So the statistical and the machine learning approaches has different algorithms to work within to predict their capabilities. And this is very important for the disaster management and mitigations. Despite the mountains terrain facing frequent and severe landslides in Himalayan regions, most predictive studies still lack updated data sets and high-resolution modeling. And then a few of them only integrate the different kind of conditioning parameters like human-induced anthropogenic actions or some real-time based hydrological data. And then limited studies compare the different machine learning algorithm, basically to see the performance, their predictive performance. So this study, we want to address these gaps by applying logistic regression and random forest models in high-risk earthquake zone of Himalaya. So the basic research question we want to address here is like, what are the most influential conditioning factors that will trigger the landslides in Himalayan regions, and compare the predictive performance of the two basic classification algorithms, logistic regression and random forest, and generate a susceptibility map, which is a useful tool for the disaster preparedness and planning. To answer these research questions, we choose the study area as the central Himalaya of Nepal. We can see in the map, our study area is near the epicenter of the 2015 Gorkha earthquake. So we can see And in order to do the modeling, the basic parameter we need is first the landslide inventory. We document the 571 map landslide within our study area, combining the 15 landslide triggering factors. And to make a model, we need to have known landslide parameters. So we generate the equal number of known landslide points based on the 500-meter buffer of the known landslide point is a 0, and landslide data is 1 for the model. As you can see in the left figure, we can see the landslide polygons with some administrative boundaries within the study area and some special location of the blaze settlements. As we see in the right map, we can see the generated known landslide points along with the landslide points that are used for the modeling. This table shows the 15 conditioning parameters that are used for the model training as well as testing, which are basically where here we introduce the many covariants that are important for landslide generation. In topographic, we use elevation, aspect, slope, plane, and profile curvature. These all are on the 12.5 and 12.5 meter resolution. Raster data basically derived from the Halas-Pulsar DEM of 12.5 meter resolutions. Coming to the hydrologic, we use stream power index, topographic wetness index, and distance to river, which are also derived from the DEM-based derivation. But the rainfall data, here what we teach is like, we take the major rainfall of last 20 years around the 8 meteorological station that is established by the Department of Hydrology and Meteorology of Nepal. And then from this raster, we did vectorize to the same resolution, and we use the real-time measure rainfall, daily rainfall data accumulated for the year. And then for geology, we use distance to fault, geology, and soil type. The fault and geology are from the Department of Geology and Mines, which are digitized and vectorized. Soil type we use from the SOTER database. And for anthropogenic, which is very important, like distance to road, land use, land cover changes, and normalized difference vegetation index, we use the data from the different sources like Department of Road, EC mode for land use, land cover, and then we calculate the NDVI in Google Earth Engine using the Landsat images. These are the covariants we prepare for. The summary of the conditioning factor, that spatial distribution of this conditioning factor are shown in these slides from the left aspect, distance to fall, distance to road, distance to stream, elevation, rainfall, TWI, and soil type within the study area. Similarly, this slide also continue the thematic rasters data set like slope, stream power index, land use, land cover. We have 11 category of land use, land cover. Geology, we have 4 different geology based on the study area, and then the NDVI and plane and profile curvatures. Now our data set is ready. This is the methodology we use for the modeling. For the preparation of thematic rasters data, we use the GIS Pro environment, and for the modeling, we use the Python scikit-learn library and utilize for data processing and modeling. For each grid, we make the model, and then it automatically abstract the data of each pixels, and then we try to use the supervised classification techniques to estimate the probability of occurrence of landslide in each pixels using the known landslide and non-landslide points for model training and testing. And then the final model is used for the predictive performance and to generate the subtlety mapping. Basically, the 2 machine learning algorithms, classification algorithms are used. One is logistic regression and random forest, as we discussed earlier. They have some different characteristics, like logistic regression is simply binary classifier, good for the linear relationship, use sigmoid function to map the probability. And then random forest is ensemble of decision trees based on the different decision trees, and they do the majority voting, and they are decide like voting we did in there. And then coming to the results, first the model performance, you can see in the ROC AUC plot that random forest has higher accuracy. And then the model feature importance, we can see elevation, distance, road, fall, slope, and rainfall are the major factors that are in the model. This is the map generated from the logistic regression. We can see the performance of the logistic regression is, and then we classified this probability of each 0 to 1 to in 5 class based on the natural breaks. And similarly, the subtlety map generated from the random forest, we can see similar performance, but some especially balanced performance from the random forest model. And then if you compare these two model performance, we can see that random forest is more stable, although they have not that kind of very discriminant dissimilarities. But if you see some especially difference, random forest is quite stable. So coming to the conclusion, our findings like the random forest model achieved the accuracy of 86% and having the area under the curve of 92, and which is outperforming the logistic regression model against the 85% accuracy. And the important thing is like the elevation, distance, fault, and then the road slopes and rainfall are the major 5 influencing parameters within the model. And 20% of the study area lies to high and very high sociality classes. And then this is very important for that we have scientific basis for the decision support system and early warning and risk mitigation strategies. And the future work can be used for the deep neural networks or deep learning models and other real-time factors for the sociality modeling. And the key takeaways from our research is like ensemble-based models are effective for landslide prediction in complex terrain like in our Himalaya, which is very important like our regions. Thank you. I'm happy to answer any.
Thank you. Any questions, please? Yeah, please.
Does it capture the... So the model you have told, does it capture the... because if one landslide would occur, the other would be having a different parameter in concern. So whether the model captures it?
Yes. Actually, after doing this research in this area, last year we have the big landslides, like eroding 3 or 4 houses and killing many peoples. And then I validate, but I haven't presented here, like the points that in the predicted performance, the high sociality area, the landslide occurs. So we validate it as well. It captures really in ground truth data.
Okay.
Thank you. Thank you for the nice presentation. If any other questions, we can discuss during the tea break. Thank you.
Thank you.
So the next presentation is by Abhijit Ajit. Yeah, please set up your thing. And then Rakesh Pillai. I think Abhijit will be presenting this. So the paper is on effect of spatial variability of permeability in rainfall-induced landslides using random FEM.
Yeah. So good evening all. My name is Abhijit and I am from IIT Palakkad, and I will be presenting on the topic effect of spatial variability of permeability in rainfall-induced landslide using random finite element method. So what is rainfall-induced landslides? Those are triggered by building up of pore water pressure in the overlying soil. So you can see as rainfall is infiltrating, the wetting front will be propagating downwards, and it will be reducing the suction in the unsaturated zone, thereby reducing the overall shear strength of the zone and triggering slope instability. And I'm from Kerala, that is the southern part of India, wherein you can see the Western Ghats is surrounded almost 50 or 40% of the state, and in 2018 itself the state was triggered by more than 5,000 landslides. And so after 2018 also we were able to see frequent amount of landslides happening throughout the year. The last one was in Wayanad district that took over for 100 lives, and thus raising a question why this is happening frequently and how, where and when it is happening. So our research was mainly focusing on addressing some of these questions, and rainfall induced landslide in Western Ghats are mostly shallow, as you can see from this figure, and hence it is idealized as an infinite slope stability. But the quantifying the risk associated with these slope doesn't lies in the idealization of infinite slope. Instead, it is actually coming in the uncertainties of the model parameters, which can be soil properties like shear strength or hydraulic soil properties like permeability, etc. And probabilistic approach actually gives a rational framework to deal with these uncertainty by you making use of these properties as like a random variable, treating it as a random variable, following a normal or a log normal distribution. We can make use of Monte Carlo simulation methods to iterate the slope stability analysis using the random variable and to get probabilistic estimates. But the real question is whether these soil properties are truly random. When you take two soil samples which are closer to each other, we will be getting almost similar soil properties, but when they are farther away, the soil properties will be different. So exactly it is not random. Instead, it has a dependence on the location. Hence, we are coined the term spatial variability of the soil, which is a significant, which plays a significant role in the entire geotechnical analysis of different aspects. So whether a probabilistic framework is accounting spatial variability, we will be able to divide it into single random variable approach and random field theory based random field finite element method. In single random variable, what happens is that in one Monte Carlo iteration, the entire slope will be treated as a single, the property will be a single property of C value or phi value based on this random distribution. But again, when it is based on random finite element method, the entire slope is discretized into small elements, and each element will carry a different value for one set of iteration itself. So the assigning of these parameters is based on a random field which is governed by certain correlation functions, and there are different function ones such as Gaussian autocorrelation function, and here you can define the you can see that it is defined based on the spatial domain x1 y1 x2 y2, and it is mostly governed by two major parameters here, that is a correlation length delta h and delta v, which governs the extent of uniformity in horizontal and vertical direction of the random field. For example, the incohesion variation of a finite slope that is considered here, when the delta value is small, that is 5 meter, the extent of uniformity is limited to 5 meter, that is, it is going to generate a little bit heterogeneous slope or a pattern here. But when the delta is elongated to 50 meter, you can see the extent of uniformity is actually getting a little bit longer, and you can see a little bit homogeneous pattern over here. So this is based on the same random variable, but at the same time it is having different behavior because of the random field. So we have tried to incorporate that random field thing into Plaxis framework, which is one of the most commercially usable FEM softwares. So we have made a framework like preliminary FEM analysis is required based on the geometry that we are setting, and we will be discretizing it into soil clusters. We will be assigning uncorrelated random properties using Python scripting, and then we will extract the coordinate as an ASCII file, which will be fed into a Python framework, which will be able to give what kind of random field we need to generate based on the correlation function. This can be easily imported onto the Plaxis framework to do analysis like coupled flow deformation or strength reduction methods and get the factor of safety estimates, and then the process is iterated using Monte Carlo simulation to get the probabilistic analysis estimates. So our key focus is mainly on rainfall induced landslide. So we are more concerned about the variability of hydraulic conductivity. So we have used infinite slope stability kind of geometry that was recommended by Ubonchi et al. For FEM softwares, especially in Plaxis. So here this is the geometry we have used, and we have only varied the properties of the soil layer on top of the bedrock. In this bedrock we have discretized into different clusters, and this will be assigned random field of spatial variability to account for the spatial variability of hydraulic conductivity, and it is treated as a log normally distributed random variable with a mean value of 1 × 10⁻⁵ meter per second, and the coefficient of variation is varied from 60, 75 and 90%, and it is treated as a stationary random field with delta at 3 meter and delta h at 50 meter. Rest all the initial condition and the constitutive models are all taken as per the deterministic Ubonchi et al. Paper. So when you look at the framework, you can see from the remote scripting we have generated, we will be able to assign a random field of permeability, do a coupled fold deformation, and get FOS as per the strength reduction method. Then we will be iterating it using Monte Carlo simulation for about 2,500. We had to iterate to get the convergence, and we will be calculating the probability of failure for each time of the rainfall that we are giving. We are actually giving a 10 mm per hour rainfall throughout the duration, and then we will also be able to get a histogram plot of the failure time as well to get the most probable time of failure. Now, when you look at the results, here this is mean factor of safety versus time, and you can see for the deterministic case by Yabonche, the factor of safety was 1.9 when there was no rainfall. As 10 mm per hour rainfall was proceeding throughout the period, by 60 hours it reached the FOS is equal to 1, the critical state. And when we were inducing coefficient of variance of 60% to permeability, we can see as the coefficient of variance is increasing, the factor of safety reduction is getting more and more faster, and it is reaching a little bit faster. Failing a little bit faster. And also the standard deviation corresponding to the mean of factor of safety is increasing with time. And for all the three cases, you can see distinct variation being shown when the when it is approaching to the failure time. So here you can see a little bit more distinct behavior with a case of probability of failure. So to understand more, I have divided it as per the US Army Corps of Engineers levels. You can see hazardous level over here with the probability of failure corresponding to 10 raised to minus 1 and you can see in about 47 hours, the COV corresponding to 90% is failing. And to understand more about it, we have actually plotted a probability density based on the time of failure. Here for lower coefficient of variance, we have a proper peak, but when the variance is increasing, you are not able to determine a proper time of failure, so there is an uncertainty associated with it. And effect of correlation length also is giving similar trend when the heterogeneity is high for little bit shorter theta v value or the delta v value as such. So here also it's the failure pattern is a little bit uncertain because of no proper peak. And coming to the conclusion, we can say that the impact of variability associated with saturated permeability is really important, as higher coefficient of variance is accelerating FOS reduction and triggers early failure and raises probability of failure. And failure timing is also uncertain when the coefficient of variance is larger, because the time of failure distribution is getting broadened, highlighting greater uncertainty and increasing risk and unpredictability. Also, role of correlation length had similar impact when shorter vertical correlation length were being considered. As for practical implication, we can say that both the magnitude, that is corresponding to coefficient of variance, and spatial structure corresponding to correlation length of the permeability field has to be considered for realistic slope stability analysis when it comes to a rainfall induced landslide. And for a scope of extension, we have developed RFEM framework to be extended to a non-stationary permeability variation, which is able to account for even weathered soil and also the impact of the climate change as well. So these are the reference, and thank you for listening.
Thank you. One quick question. Yeah, please.
Very good presentation.
Thank you.
Yeah. So I have a question. Where is the water table? Two questions actually. Where is the water table? And how did you limit the suction minus 50 to minus 80 kPa in plexus?
Actually, the initial water table was set in such a manner that it is actually set below the bed level to get that same variation as per the Yabonji paper. Then the water table is water table is allowed to develop over the bedrock as the time proceeds.
Okay.
Yeah.
Okay. Thank you.
Okay. So the next presentation is by Yamini Jala. That is on numerical analysis of piles placed on sandy sloping ground considering hardening soil model.
Okay. Good afternoon, everyone. I am Yamini Chala. Today I am going to present my topic on numerical analysis of piles placed on sloping ground considering hardening soil model. And as we all know that pile foundations are the thin structural members which are used to transfer load from the structures to the strata below the ground level. And these are some of the places where we use the laterally loaded piles. And without any delay, I am going to tell that in this current study, my main aim is to know the what is the effect when the piles are placed on different positions on the slope and also away from the crest. So these are the two different sides that I am showing. This is whenever I mention that negative S by D, that corresponds to the piles on the embankment side. And whenever I say that S by D is positive, that corresponds to the piles on the sloping side. And along with that, I have also mentioned the parameters that I have used in this study. And for this whole study, I have used the Plaxis 3D software. And here the pile is considered as a linear elastic material. And these are the steps that I have followed for modeling my whole soil strata. Initially, my soil layer, whatever is the sloping ground that you have seen earlier, that has been generated by using the different boreholes. And then in the structures mode, I have developed the pile, whatever the lateral load I have given. And after modeling everything, I have done the mesh generation. And here we have, we have done sensitivity analysis. We have changed the type of coarseness of the mesh and finally decided to use the medium coarse mesh in the current study. And then later the flow conditions are generated in this mode. But in the present study, my water table is far below the ground level. And then later in the stage construction, as per the requirement, I have initiated all the phases and then calculations are executed to know the results. And in the current study, I have considered the empirical formulas used by Bringreve et al. 2010 in order to validate the how effective these parameters are. I have considered the laboratory study by Muthukumaran 2014, and I have tried to simulate his study in Plaxis 3D, and I have found that the laboratory study and the Plaxis study is almost the same. And from this, I can say that the parameters that I have used in this study can be further elaborated and can be used. And in this study, I have tried to give a lateral displacement at the pile head, and it is limited to a value of 0.2d. Here, the diameter I have used in this study is 0.8 meters. So whatever in this total study, I have used a lateral displacement of 0.16 meter at the pile head. And then later, I have found the lateral pile capacity that I have stated as ultimate lateral capacity of the pile. And these are some of the results. Here I have varied the ground slope, 0 degrees corresponds to the level ground. And I have varied the slope like 10, 20 and 30 degrees. And as we all know, when I have made a lateral displacement of 0.2d, that is nothing but the 0.16, you can see the amount of decrease in the lateral capacity as there is an increase in the ground slope. Here I wanted to specify what is the amount of reduction in the lateral pile response. Here it is shown in the lateral load capacity, and here in the right side it can be seen in the form of normalized bending moment. Here the bending moment is normalized by using the ultimate lateral capacity and the length of the pile considered. Here the length of the pile is 24 meters. And here it can be seen for the various ground slope. As the ground slope is increasing, the bending moment is increasing. And here it can be clearly seen this is the ultimate pile capacity. As the ground slope is increasing, the value of lateral pile capacity is decreasing. You can see the amount of reduction from the level ground to the sloping ground, and this is the amount of increase in the bending moment. And you can also see this Z max by D is nothing but, this Z max by D corresponding to the shift in the maximum bending moment. As we see that when it should be the second digit also should be there. When we see that when it is shifted from level ground to sloping ground, the maximum bending moment, point of maximum bending moment also shift downwards. And then here you can see all the different cases that I have considered in the study. Here we are comparing the pile on the embankment side and also the sloping side. Here A, B, C, D correspond to the pile on where S by D is from -4, plus or minus 4 to plus or minus 16. And this is the amount of lateral pile capacity that is shown. And here this is the case for the critical slope 30 degrees. And here it can be seen that the lateral pile capacity is decreasing. Here you can see the black line corresponding to the level ground. And you can see the amount of decrease when the pile is on the slope side. And similarly, we can also see the normalized bending moment for all the different cases. And you can see the amount of increase in the normalized bending moment when pile is shifted from the crest to the different positions along the sloping ground. And here it is the total table showing the difference in the positions. The amount of lateral pile capacity, maximum bending moment, and the shift in the maximum bending moment position for various positions. And towards the conclusion, I just wanted to tell that when there is a change in ground slope, I just told that it is lateral capacity is decreasing and maximum bending moment is increasing. This is because of the decrease in the passive resistance when there is a change in the ground slope. And I have also changed the distance from towards the crest on the left side and also towards the right side. And I have also varied the ground slope. So in this, it is a part of my whole study. In this, we wanted to show the effect of passive resistance. And these are the references I have used for my study. Thank you.
Okay, any questions?
Did you validate your work with some benchmark studies or just like modeling?
No, I have validated this one. I have validated with several studies. Only here I have shown this. I have validated with Rees et al. Study and also...
Like a real benchmark?
Not... I have validated with laboratory studies.
Okay.
Laboratory studies.
Field level benchmark?
No, laboratory studies.
Okay, anyone else? Okay, thank you, Yamini. So the next presentation is by Ratnakar Ramesh Mahajan.
I will take care.
Okay. Okay, thank you. So that is on analysis of erosion control methods and soil loss estimation using the Russell method.
Yeah. Thank you to all for coming to this session. Let me have a look briefly on the method that will be covered by our presentation today. After a brief introduction on soil erosion processes, we'll go through the classification provided by the relevant ISO standard regarding erosion control solution. Then we will go through the design approach based on the Russell equation, and we will close with an application of the design approach based on the Russell equation. Soil erosion is a soil degradation process consisting in the detachment of the topsoil due to the action of the eroding agents. When soil is detached, then it is transported away. This process occurs in a geologic time scale, but when human activities alter the landscape can be greatly accelerated. The two most common causes of soil erosion are water and wind. Water in the form of rain causing the displacement of the soil particle close to the surface, and runoff that can be cause of the carving of small rills and channels on erodible soil. On the other hand, strong winds can bring in suspension the fine particle soil, instead of the larger one can be moved by bouncing and rolling mechanism. Usually, vegetation, if well established, is considered a sufficient protection against erosion, since vegetation cover can provide a physical protection of the soil surface, and the root apparatus can hold in place, preventing that soil will be blown and transported away. Based on literature data, an 80% of coverage, vegetation coverage for clay soil and 70% for sandy soil is usually considered as sufficient protection. But even if reachable, this percentage, there is anyway a time window until the full development of the vegetation, when the slope is at the risk of erosion in case of intense rainfall. That's the reason why there are available many erosion control solutions to protect soil from erosion and creating favorable conditions to the development of the vegetation. Within this solution, geosynthetics emerged in the last year, in the recent years, as a cost-effective and sustainable solution. Let me have then a look on the classification provided by the relevant ISO standard 18228 part 8 is still under publication. It's not yet been published, but geosynthetics addressed to erosion control solution can be classified based on product configuration, that means MET, GeoGrid, web, and so on, based on the origin of the material, then substantially based on synthetic and natural material with the related performances, and the duration of the protection. We have permanent erosion revegetation materials with the acronyms of PERMS, and temporary erosion revegetation material with the acronyms of TEM. Both of them work as a system in combination with soil and vegetation in order to protect soil from erosion. But in the first case, regarding permanent erosion and vegetation material, geosynthetics are called to provide a permanent protection thanks to their long durability. Instead of for terms for temporary erosion or vegetation material, they are called to provide, to create, to build up the favorable condition to the development of vegetation that will be itself the protection of erosion. Typically, erosion control solution design suffer from a lack of scientific rigorous approach. Typically, the selection of the erosion control products is based on knowledge, on lessons learned from past projects. Instead of monitoring and modeling an erosion control process can help in identify the reason behind the erosion process and in supporting in the identification of the proper solution, the mitigation solution, restorative solution to be applied. The Russell equation that has been issued in the late 60s by the US Department of Agriculture is the most common model used to model erosion control process. It's a universal format requiring the evaluation of the factor included in the formula based on specific statistic evaluation on local basis. It provides basically the soil loss with reference to different factors. R factor is the rainfall runoff erosivity factor, K is the soil erodibility factor, L and S are the slope length and slope steepness factor. C, the most important one, is the cover management factor, and P, the support practice factors. Let's have a look on each of them. R, rainfall and runoff erosivity factor depends on local regional rainfalls that so can be estimated strictly based on pluviometer readings, but there are many empirical formulas providing an estimation of the R factor. Then K, that express the tendency of the soil to be eroded, is directly correlated to the soil texture, so the different percentage of clay, gravel, sand, and so on, and the hydraulic conductivity of the soil. L and S, no need to go deeper on this, reflect the configuration of the slope in terms of length and inclination. The C factor, the most important one, that can be only obtained through full-scale or large-scale laboratory test according to the relevant ISTM 6459 norms, provide the impact of the vegetation and the erosion control technique. It means in our case geosynthetics, that they are installed on top of the slope. And finally, P factor is the support practice factor, reflect agriculture landscaping technique that usually is taken equal to 1, neutralized in construction project. Just having a look on the application of the Russell equation, I will finish in 1 minute. Just having a look on the evaluation of the soil loss based on the Russell equation for an hypothetical road project in India, referring to a slope having a length of 7.81 meter, an inclination of 33.7 meter for an coverage area of 7,000 square meters, considering a duration period or an evaluation period of 1 year, we can have an evaluation of the soil loss for the bale soil unprotected without anything on the top. There will be 570 tons for the 1 year period. Instead of protecting the same slope with the material proposed by our company, it means a geomat reinforced with a polymeric geogrid, will be 14. You can see the difference in terms of reduction according to the soil loss. Let me conclude briefly. As you have seen, there are many solutions to protect the slope and create favorable conditions to the development of vegetation. There is a lack in the design, a lack of scientific approach in the design. That's the reason why applying a design method based on the Russell equation, we can have a guidance and a support in the selection of the proper material to protect slope from erosion. But Russell equation, specifically the R factor, relies on different factors based on statistical analysis. Further studies are requested in order to incorporate the effect of the climate change in this evaluation, in order to obtain reliable and consistent evaluation of the soil loss. Finish.
Thank you. Is there any questions? Okay.
Not clear or too boring?
Okay. Our next presentation is by Sri Krishnan Shiva Subramaniam on soil water index thresholds for territorial landslides, early warning systems in India.
I'm Sri Krishnan from IIT Roorkee. I'm very glad to be here in front of you all. And today I'm going to share some insights about the ongoing research work between IIT Roorkee and Hokkaido University in Japan. This is a part of a research project, and the contributing authors are here, both from both the institutes as well as ISRO India. So we do have this landslide problem in India, both the shallow landslides and debris flows. And currently, India is into developing forecasting system for landslides. And if you are aware, last year there was this inauguration of NLFC, last to last year, which is headquartered in Kolkata. So let me explain. This is the presentation outline. I will skip this. And we all are well aware of the problem of landslides and what it does to the people and as well as the economic and transportation disruptions. So if we look specifically into the landslide problem, it is a scale-dependent problem where we do have landslides, that one landslides or two landslides happening at the scale of, let's say, 1 meter to, let's say, 100 meter, 10 meter to 100 meters. So that is at the slope scale. Whereas we do have like catastrophic conditions, mainly by rainfall, where a catchment, a hydrological boundary experiences few instances of landslide of a number, let's say 1,000 such so. But whenever this disaster strikes, whenever the hazard experiences into a larger catastrophe, we do have 1,000 number of landslides all across the hill slopes. So for the government, for disaster management, we have a bigger mandate to inform people before a landslide happening. That's why we need to have early warning system at this scale. So this is the territorial scale. And I'm going to tell the territorial scale landslide early warning systems especially. But for the territorial scale landslide early warning systems to work, we need to have an understanding of landslide at the slope scale as well as the hydrological control at the catchment scale. So what we need to do, of course, we cannot study everything at the slope. So we do laboratory experiments using reduced scale flume and all. This is the overall story. So this is the conceptual diagram of a rainfall-induced landslide, both the shallow landslides and debris flows. And the argument here is the landslides, more or less the shallow landslides, are not driven always by positive pore water pressure. Instead, the loss of matrix suction contributes to the landslide activity. In case of debris flows also, saturation is often happens. But before the saturation also, the initial moisture content can have a larger say in the triggering and as well as the volume of debris flow. So we do have few variables which can inform us about the occurrence of landslide, let's say an hour or 6 hours before. But we need to have this information through some proxies at the territorial scale so as to forecast landslides at the regional level. So some understanding is required, and a global outlook of the territorial scale landslide early warning system tells us there are two kinds of thresholds that are used for forecasting. Mainly the intensity and duration threshold, which only considers the meteorology of the landslide cause, that is the rainfall. And currently we have this system in India, that is the National Landslide Forecasting System by GSA, which also uses the meteorological threshold, that is the intensity and duration of rainfall. We can also see other countries. So in this sketch, whatever is showed in blue uses the ID threshold. But we do have a problem here. We are not accounting for what is happening on the slope. We are forgetting the hydrological component, that is the soil moisture. If we look into the developed nations, they also have some complex thresholds, which is based on hydrology as well as meteorology, that is the hydrometeorological thresholds. So one such nation is Japan, where they use the soil water index criterion. Soil water index means a proxy of soil moisture, which we can forecast at the regional scale. So our purpose here at the IIT Roorkee, we are collaborating with Hokkaido University to see whether can we use the soil water index thresholds for forecasting of landslides in India. But we do have a larger problem that the landslides happening in Himalayas as well as in Western Ghats more or less is not the same what Japan experiences. We have the geological heterogeneity as well as the climate heterogeneity, so we need to test. So we start from the slope scale. So we do reduced scale flume experiments. Sorry about the text, I don't know that it will change, so it was a better text while looking at the presentation. So here it is not that good, my apologies. So we took debris material from active debris slide sites in the Himalayas to see whether the unsaturated behavior has a say on the triggering of debris slides by rainfall. And this experiments revealed us, yes, there is some kind of consideration of unsaturated soil shear strength, which actually impacts the instability of debris slides in the Himalayas. But this experiment is done for only one debris slide site, considering the uncertainties, whatever we can hold. So with this, we know that the models using infinite slope stability as well as the normal hydrological models will work for debris slide as well. We got the confidence. And we do have some developed numerical models which works on the catchment scale, a hydrological boundary scale, for shallow landslide as well as debris flows. So our intention here is to use these models to test, to develop scenarios that account for conditions which have triggered landslides in the past, and then see whether the soil water index threshold will be able to predict the landslide or not. So this is the approach we followed for the numerical modeling. And we started with testing it in a site in Uttarakhand. So we have done field visits. Sir? Okay. We started with Kedarnath. So how much time I have said? It's already 8? 2 more minutes. Yeah, I'm almost near to the conclusion. So this is the intensity duration threshold, which we have developed using the numerical model. As we can see, the existing thresholds were on the daily scale, whereas the new threshold we developed is on the hourly scale. And the 2024 Wayanad landslide is also given. And with the testing of soil water index also for the same Uttarakhand, this is the method we have used. So we have seen that the soil water index is also applicable for forecasting of landslides in India. More or less, it improves the predictive capacity of the existing early warning system, which only uses the meteorological threshold, whereas our system uses the hydrometeorological threshold. So this is still an ongoing work, but it is working for Uttarakhand. We are yet to test for other case studies. So with this, I conclude my talk. Thank you. Open for some discussions. Thank you.
Any questions?
Very nice work. I'm really interested in this kind of work. But I have one simple question. If you do for regional scale, like the ID, only the threshold kind of things, this is also going to be some kind of biasness. So what I want to say is like, did you validate this SW index with any other data? Like
yeah, we have validated with case examples from Japan, and we have validated it for a hindcast mode for 2013, year 2013 landslides in Uttarakhand. And to account for the heterogeneity, we do sampling at the different lithologies across sites in Uttarakhand. But that we did for only the Kedarnath catchment, not at the entire state of Uttarakhand yet. The heterogeneity is more or less accounted for. Yeah.
Accounted.
Yes, yes.
And then, sorry, we'll talk later.
Okay.
Okay, other question I have is, you said it's nothing related to the pore water pressure, but only matrix suction.
Yes, sir.
But
So
matrix suction is also nothing but negative pore water pressure.
exactly, exactly. So what we want to mention here is, thank you for bringing up the clarity, sir. Usually there is an observation that only positive pore water pressure drive the instability. But even the loss of matrix suction, even before it reaches to positive pore water pressure, the instability do occur. We have seen it in the example of the Flume experiments. So loss of matrix suction instead of positive pore water pressure. So, but pore water pressure is there. Negative is also positive. Thank you.
Okay, thank you. Thank you, Subramanyam. So, perhaps the last presentation is by Revati Manohar. Yeah. The title of the presentation is Effect of Stress Anisotropy on Shear Strength Parameters and Infinite Slope Stability, a numerical approach.
Good afternoon all. Myself Revati Manohar. I'm a research scholar from IIT Hyderabad. So today my topic is Effect of Stress Anisotropy on Shear Strength Parameters and Infinite Slope Stability, a numerical approach. So first of all, let me give a brief introduction about anisotropy. Anisotropy indicates the directional variation in soil property. So it occurs due to various reasons like past depositional history, the loading condition, or even due to the microstructural properties of the soil mass. So anisotropy can be broadly classified into two: inherent anisotropy and induced anisotropy. Inherent anisotropy is an intrinsic material property, whereas induced anisotropy, as the name suggests, it is induced on the soil mass due to some external load or stress acting. So the main effect is that anisotropy will strongly influence the shear behavior as well as the deformation properties of the soil. Now let's see how anisotropy is applicable in case of slope. So here you can see an infinite slope. Also the failure plane is depicted there. So when you observe the element along the failure plane, you can see it is having a triaxial compressive stress state near the face region. But as you move down along the failure plane, this stress state is changing from compressive to extension. So this reversal or the variation in stress is referred to as stress-induced anisotropy. So what is the effect of this anisotropy is that this will alter the mobilized shear strength of the slope, and thereby it will reduce the factor of safety. And in case of a slope, there is inherently gravitational loading acting, and this is causing this anisotropic effect. So coming to the motivation of the present work, actually almost all the practical slope models ignore this anisotropic effect. And few advanced numerical models have evolved. They are constitutive model behavior, but they have there is a requirement of direct experimental validation, especially at the element level. So coming to the present research objectives, this present study aims to quantify the effect of stress-induced anisotropy on shear strength parameters, also to study its influence on the stability of infinite slopes. So for this purpose, we are considering a soil element along the failure plane in the compressive zone as shown in the picture, and we are doing numerical modeling using Abacus, and the same model is validated experimentally using advanced triaxial testing. And the results from this numerical method and experimentally validated the results, we are using this in a real case slope scenario. So coming to the numerical modeling part. So here we are using shear strength reduction technique, meaning we are progressively reducing the soil shear strength until failure. So for this purpose, we are modifying or reducing the shear strength parameters using a reduction factor RF. So this non-converging RF value will be interpreted as the factor of safety of that particular slope. Now coming to the modeling part in detail. So I have already explained we are considering a soil element along the failure plane, that too in the compressive region. So here you can see the element here, the properties, material properties and other parameters are considered same as that of the experimental study. So here actually I am having a triaxial cylindrical soil specimen having 38 mm diameter as shown here. So the same is modeled in numerically. So since this is an axisymmetric specimen, we are modeling only 1/4 of the domain. Boundary conditions are also indicated. Now coming to the test condition, we have two cases, isotropic case and anisotropic case. So to bring in this anisotropic effect, we are defining a new term called anisotropic stress ratio, Kc. So it is nothing but the ratio of principal stresses, that is sigma 1 by sigma 3. So for maintaining isotropy, we are having Kc value equal to 1, meaning sigma 1 will be equal to sigma 3. Whereas for anisotropic case, we are maintaining Kc such a way that sigma 1 will not be equal to sigma 3. So in this present study, I have considered Kc value as 3, and that is the assumed average based on various laboratory test results. Coming to the modeling part in detail. So first is the geostatic step where we are applying confinement to the soil specimen, and next soil step we are applying the undrained shear. So here you can see the displacement contours from anisotropic test conditions. So the result I will explain in the coming slides. Moving to the experimental validation part. So here we are validating the compressive stress element in a triaxial testing as shown here. So the material used is river sand with properties tabulated here, and gradation, it is a poorly graded sand. So here also we have two test conditions, isotropic and anisotropic. So for that I am doing an isotropically consolidated undrained test and an isotropically consolidated undrained test. So in this experimental setup, in order to bring in anisotropy, we are using a programmable stress path module through which we can input the Kc values through P and Q. Coming to the results. So here the stress strain variations are presented here for both isotropic case and anisotropic case. Both numerical and experimental results are there. The most important observation is that for an isotropically consolidated specimen, they have mobilized higher peak deviatoric stress compared to anisotropic one. And you can see the variation or the reduction, percentage reduction is around 20%. So this confirms that stress-induced anisotropy significantly reduces the shear strength. Here again you can see the stress path variations for anisotropic case for both experimental and numerical studies. The most important observation is the factor of safety. Here I have calculated factor of safety using the conventional analytical expression C plus sigma 10 phi by tau, that is resisting force by driving force. And you can see the tabulated results in table 2, experimental and numerical results. The values are closely matching. A slight variation is observed, which is probably due to the boundary condition, experimental uncertainty, or even due to dilatancy, since it is a sandy specimen. So the most important observation here is the reduction in factor of safety. It was observed that around 20 to 23% reduction was observed due to anisotropic effect. Now, another important observation that we found is that the shear strength parameter variation. It was observed that the friction angle was reduced by 4 to 5 degrees, attributing to the anisotropic stress conditions. Now, let's go to the application part. Whatever results we have obtained so far, that is the experimental as well as numerical results, we are applying into a real slope stability analysis. And for that, we are considering a real slope in Kavalappara, which is in Kerala, a region prone to rainfall-induced landslide. So you can see the geometry as well as boundary condition given there. And the material properties, it is lateritic silty clay, and it is adopted from literature. So here also we are modeling two scenarios, isotropic case and anisotropic case. For this isotropic case, we are using original soil strength parameters. Whereas coming to anisotropic case, we have reduced the shear strength parameters by a percentage. And that percentage is exactly from the previous section, the results we got from the previous section. Coming to the results. Here you can see the displacement contours under anisotropic conditions. So it is observed that the maximum deformation is concentrated in the toe region. That indicates there is a likely zone of instability under anisotropic stress in the toe region. Further, in the second figure, you can see the onset of localized plastic deformation occurring near the crust, and in the enlarged view, you can see the early stages of failure initiation. This is actually not a failure analysis. We are interested only in showing the effect of anisotropy, how it is affecting the slope stability. That's why here we don't have a well-defined failure plane here. Also, this is an infinite slope. So coming to the FOS results comparison table, you can see. So the most important observation is the reduction in FOS. Here also it was observed that a reduction of around 7.5% was observed. And this indicates that if we consider the effect of anisotropy, there is increased susceptibility of slope failure. Meaning this is more valid in case of critical slope, which is at the verge of failure. So there is a requirement to consider anisotropic effects. So these are my conclusions. Thank you.
Okay. Any questions? Yes, please.
Hi.
I'm Vishek Kozov. I'm from IT Kharagpur. So I just have one question.
Thank you. So the question is, what kind of soil are you trying to model here? Is it a coarse grain sand or it's in the fine grain sand?
Poorly graded sand, SP.
Poorly grained sand. Yes. The purpose of asking this question is number of recent studies, they tried to solve this anisotropic thing, particularly in a coarse grain soil, using fabric anisotropy, right? So there are the granular materials. So why, if I may ask, like why you have opted to go for a stress-induced anisotropy rather than a fabric anisotropy? Because in a stress-induced, as much as I have understood, it's like you are reducing the shear strength parameter based on a certain laboratory test results. Correct. Right? So what's your opinion, what's your take on that? How far this will be accurate in the comparison to such models?
Yes, most of the studies actually it is focusing on inherent anisotropy. That means material property, inherent material property. And this stress-induced anisotropy is a different type of anisotropy which is mostly overlooked in most of the studies. So in order to have more reliable estimates, as I have given in the limitations, we need to have combined effect of induced and inherent anisotropy so that we will get the complete idea how it will be reducing the overall slope stability.
But the formation of the fabric can be because of the inherent or like the deposition that has taken place over the years, as well as because of the stress history as well, right? So for a coarse grain soil, my point is it completely like decoupled or they are kind of contributing to the same thing?
It is, in effect, they are contributing the same thing, but it is two different phenomena. Inherent is different and induced is different.
Okay.
Yeah.
Okay. Thank you. Thank you.
Any other questions? I have just one quick question. What is the K value that you considered in ACU test?
Permeability, sir.
No, like the stress ratio.
K not, KC, 3.
3.
Yes.
So I just observed your M value is 1.8. That is very high. It should be around 1. And then K is also 3. That is also very high to start with. It's like you are starting with a failure condition. So,
Sir, this is actually part of my study. It's actually, varying.
yeah.
Yeah.
So maybe something to look at it.
Yeah.
Okay. Thank you.
Thanks.
So now I would like to invite Professor Tyagaraj to just summarize the session.
Yeah, so good evening. I think hall is full. Meaning is it's very interesting session. So everyone is very attentive, and I'm sure that you all agree we had very meaningful technical presentations. So on wide variety of topics on slope stability and landslides. Slope stability is open pit mine slopes, right? Slopes for railways, and also we have had some topics on wind erosion mitigation methods, both in terms of some experimental results and in terms of methods. And other than that, we also had territorial landslide early warning system, something like that. So, and laboratory studies, of course, very interesting. So with this summary, I conclude, and once again, let me congratulate all the presenting authors. Many congratulations, and theme lecturer also for the nice presentation. So with this, I conclude this session and hand over it to the organizers. Thank you.
Now I invite Professor Hari Krishna Padavala, our theme lecturer for the day, to the stage. I request Professor Tyagaraj and Professor Sumit Kumar Sinha to hand over the memento.
You don't cover the
Thank you. So please stay. Please stay. I request Ratnakar Mahajan, Technical Head India, Southeast Asia and Pacific, McAfee, to hand over the memento to our chair and co-chair for the session. I would like to thank Professor Tyagaraj and Professor Sumit Kumar Sinha for chairing and co-chairing the session today. And I would like to extend my gratitude to Professor Hari Krishna Padavala for the interesting thematic lecture for the session. And I would like to thank all the participants and the audience for the active engagement and interest in this session. Thank you. I request all the participants to join for a group photo.